Hi, I'm Zor. Welcome to Unizor education. I would like to continue talking about matrix determinants. I did spend some time on 2x2 matrices, and let me just remind you very briefly, if you have a system of two equations with two variables, and I'm talking about linear equations, of course, then the matrix of coefficients, which has two rows and two columns, it has an expression a11 a22 minus a12 a21 as a very important characteristic of the matrix. Now, this characteristic actually is so important that whether it's equal to 0 or not is sufficient to determine whether the system has a unique solution. So if this is a system of two equations, we are talking about unique solution. If this is a transformation of coordinates from x coordinates to y coordinates, then this basically is equivalent to whether the transformation is inversible. I mean, if you can find out x1 and x2 as a unique solution based on y1 and y2, that means we can transform it back, right? So from x to y, and then if y is given, then we can transform it back to x. So this matrix of transformation, now it's a transformation of coordinates, is again, it's important, and this particular determinant, whether it is or it is not equal to 0, is a characteristic of both the system of equations or matrix transformation of the coordinates. Basically, I might actually say that if this determinant is not equal to 0, then the matrix is, well, good in certain way, because the unique solution of the system exists, or the transformation, linear transformation, is inversible. If the matrix has the determinant equal to 0, then the system is not good. I mean, I might say it's bad. Basically, it means that system either doesn't have a solution, or there are infinite number of solutions, but in any way, there is no unique solution, let's put it this way. And the transformation, which is defined by this matrix from x coordinates to y coordinates, is not inversible. Now, what's not inversible? What's inversible and not inversible transformation of two coordinates? It's on the plane, basically. Well, for instance, if you want to stretch the plane, so every vector is multiplied by 2. That's a linear transformation, and it's inversible. Basically, it's like y1 is equal to some coefficients times x1, and y2 is equal to the same, for instance, coefficients by x2. However, if you have a projections, for instance, like y1 is equal to x1 and y2 is equal to 0, for instance, right? So this is not really a good transformation, because lots of different vectors are transformed into the same one if their projection is the same, right? So this is not a good transformation, right? So determinant equals to 0 means it's not a good transformation, and it's not a good system of equations. Now, I would like to basically do exactly the same with a three-dimensional case. So I have three coordinates. My system of equations looks like this. So my matrix of transformation is 3 by 3 instead of 2 by 2. And the question is, does this matrix of the coefficients a11, a12, etc., which has 3 rows and 3 columns, does it also have this particular characteristic like a determinant for 2 by 2 case, which would be again a very indicative of whether this transformation of coordinates in a three-dimensional space is good or bad, whether it's reversible, so to speak, or whether the system of equations has a unique solution. So either or, we are talking about the matrix from these coefficients, A with indices, and the question is it good or bad, and how to determine whether it's good or bad, and is there anything like a determinant for a two-dimensional case which would help us to determine this particular quality of the matrix? Well, first of all, the answer is yes, there is such a characteristic, and it's called exactly the same way. It's determinant. So the question is, what is determinant for a matrix which has 3 rows and 3 columns? So what I'm going to do is I'm going to solve this particular system of 3 equations, and in the process of solving, I will basically determine if I can solve it and it will produce a unique solution, then the system is good. And if there is some condition when I cannot do this, then that would be a condition which I'm looking for, and that would be a formula for a determinant. What's the condition on all the coefficients? The formula basically which combines them together in an expression which either equal to 0 or not equal to 0. So if it's equal to 0, same as a 2x2 case, I will say that the system is not good. And if it's not equal to 0, the system does have a unique solution, or transformation of 3-dimensional space is reversible. So how can I solve it? Well, first of all, let me just assume that this is a true system of 3 equations with 3 coordinates. Now, for this, I need at least one of these coefficients not to be equal to 0, because if they're all equal to 0, then it's definitely a bad system, because it has 3 equations with only 2 variables, and it's either doesn't have any solutions or it has 0 solutions basically, or it has some infinite number of solutions, or the equation, one of the equations is basically a linear combination of 2 other equations, which means we still have a 2-dimensional case. We have 2 variables, independent variables. So I assume that one of these for x3 is not equal to 0, and just for definitiveness I assume that a13 not equal to 0. All right, at least one of them should be not equal to 0. Now, how can I solve it? Well, here is my plan. First, I will reduce this system of 3 equations to the system of 2 equations with 2 variables. I will eliminate x3. How can I do it? Well, if I will multiply the first equation by a23 and the second equation by a13 and subtract, then my x3 will cancel, right? And then I will do the same with the first and the third one. I will multiply by a33 and then I'll multiply by a13 and again subtract, and again I will have another equation. In both cases, x3 will cancel out, and I will have 2 equations with 2 variables, x1 and x2. All right, so first of all, let's multiply this one by a23 and this one by a13. All right, and subtract. From the first, I will subtract the second. So what will I have? Well, I will have, on the left, I will have b1 times a23 minus b2 times a13. Well, my most important problem right now is not to make any mistakes, because there is a lot of calculations here which are kind of tedious. But I would like actually to mention that tedious and long calculations, they also have their purpose. Think about Winter Olympics, for instance. You have skiers, cross-country skiers, who are going for like 50 kilometers. Do you think it's fun? I guarantee it's not fun, but it kind of develops your stamina, right? So all these long distance calculations develop the stamina for your brain. So brain also has a stamina. You have to really be, persevering. All right, so the left part I have just done. Now the right part would be, now the x1 coefficient will be a11 times a23 minus a21 times a13, right? So a11, a23 minus a21, A13. That would be x1. And x2 would be A12, A23, this times this, minus this times this, minus A22 times A13. That would be x2. And x3 will cancel out, because it will be A13, A23 times A23, minus A23 times A13, so it's 0, right? Okay, fine, this is done. Now let's do another thing. We will multiply this by A13, and we will multiply this by A33. Now, the first and the third, and then we will subtract them. My x3 will again cancel out. Now, what would be on the left? On the left, I will have b1 a33 minus b3 times a13 equals to a11 times a33 minus a31 a13, that would be x1, and coefficient at x2 would be a12 a33, this times this, minus this times this, minus a32 a13 x2. Alright, so now I have reduced my 3 equations with 3 variables to 2 equations with 2 variables, right? So now, well, I can solve it, but at the same time I can actually use the previous results. You remember we were actually researched the system of 2 equations with 2 variables, and we found that the determinant of the matrix of the coefficients is basically a decisive factor. If it's equal to 0, then we have a problem. The system does not have a unique solution. So if my determinant of this system is equal to 0, basically I will have some formula for all the coefficients of my initial matrix, and if it's equal to 0, that means basically that the system does not have a unique solution, right? So I will just use this. So my determinant for this system is this times this minus this times this, right? That's the determinant. The main diagonal minus alternate diagonal. Well, and again, now my most important problem is not to make mistakes, because I have to make a lot of multiplication, etc. So just bear with me. I hope I will not make a mistake, but any case. So this times this, that would be 4 different members. This times this first. So I will try to order them in a sequence of the first index. So it's A11, A23, A12, and A33. So I will use A11, A12, and then A23, and A33. That's my first member. Now, this times this would be with a minus sign, A11, then A13, A23, and A32. You see, I'm ordering these in the order of the first index, and if the first index is the same, then ordering in the second. Alright, next I multiply this by this, and that's a minus sign. Now first I will have 1, 2, 1, 3, 2, 1, and 3, 3. And finally the fourth member is with a plus sign, because this is minus and this is minus, so it's a plus. This and this. I have 2 actually, 1, 3. Then 2, 1, and 3, 2. All right. So this is this multiplied by this. Now I have to subtract this multiplied by this. So it's minus sign. Okay, first by first, so it's 1 1, 1 2, 2 3, and 3 3, right? 1 1, 1 2, 2 3, and 3 3. Okay, that was with a minus sign. Now this times this, it's minus, but then since I have minus in front, it would be plus. The smallest one, 1 2 index, then 1 3, then 2 3, and 3 1. Now this member times this. Now this is a minus, but there is a minus in front, so it's plus. 1 1 would be the smallest index. Then 1 3. Then 2 2. And then 3 3. Finally, this times this, it's a plus, but there is a minus in front of it, so it would be, in the game, there is a double 1 3, and then 2 2, and 3 1. I think I did not make a mistake. I hope, at least. So, what can we do about this? Well, this is an expression of the determinant of this particular matrix, right? So if it's equal to 0, I'm in troubles in the sense that the whole system does not have a good solution, right? So I actually can just analyze this, and but before equating it to 0, before actually researching this stuff, I would like to simplify it a little bit. And here's how. Well, first of all, I see that there is something which is supposed to cancel out. The first one and this one, you see, they are the same. Cancel out. Plus and minus, all right? Now, what's interesting is that all other members contain A13 as a factor. You see, A13, 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 and A13, okay? So, I have basically assume that A13 is not equal to 0 because I had to assume that one of these coefficients is not equal to 0, right? So if I am asking whether something is equal to 0 or not, and I can factor out A13 which is not equal to 0, so whatever will be left after I factor it out is supposed to be either equal to 0 or not, because A13 is not equal to 0, which means I can basically consider, instead of this particular expression, the one which is this divided, factored out one A13, right? So without A13. And I will also do it just regrouping. First I will get all pluses, and then I will get all minuses, right? So all pluses are, and I will try to arrange it again in sequence. This plus, and this plus. This is the smallest A11, so I will start with A11. Now A13 would be factor out here, 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 and here. All right. So I will do it without A13 now because it's not equal to 0 anyway. So A11, A22, A33. That's one. Then I will have this one with a plus sign, because it has the first one A12, and I'm trying again to be in sequence. Oh no, there is no A13 anymore. Yes, A23 and A31. So this is done, and this is another with a plus. A13, A21, A32. Okay. All pluses are done. Now all minuses. Minus. So this is the smallest index, so it's minus A11, A23, A32. Now this is minus A12, A21, A33, and this is minus A13, A22, A31. All right, so let me wipe out everything else, and basically I do have the expression which I can consider as a very important characteristic of the matrix of the coefficients. If this expression is equal to 0, then I can say that my system does not have a solution, does not have a good solution, unique solution. All right? Now, and this is actually, by definition, the entity which is called determinant of this matrix. So I know that if this is equal to 0, my matrix does not have, my transformation is not a unique transformation, my system of equations does not have a unique solution, etc. Right? So let me just talk about this particular expression. It looks a little bit, well, cumbersome, I don't know, complicated. However, I would like actually to show you the geometry of this thing. That would make it easier to understand actually how it's all done. Now, let's just put it in perspective. This is a matrix of coefficients. The interesting thing is, I actually do remember by heart this formula. I'll just show you how I remember it. Now look at the three positive members. Now this one is main diagonal, right? A11, A22, and A33. So we start from the main diagonal. Now A12, which is this, A23, which is this, and A31 is this. This is a triangle which has a short side parallel to the main diagonal. Now this one, 1, 3, which is this, 2, 1, which is this, and 3, 2, which is this. This is another triangle with a short side parallel. All right? So all positive members are the main diagonal and two triangles with the short side parallel to the main diagonal. Now let's talk about the negative sides. Okay, we start with this. Now it's A11, A23, which is this one, and A32, which is this one, right? Okay, I have the red one. So it's this triangle. 1, 2, 2, 1, and 3, 3. This is this triangle. And finally, 1, 3, 2, 2, and this is the alternate diagonal. Now, all negative members are alternate diagonal, and again, two triangles with a short side parallel to it. So if you just draw this particular matrix as a square, basically, so two diagonals, main diagonal with the plus, alternate diagonal with the minus, and then everything which is parallel, all triangles which is with the side parallel to main diagonal are with the positive sign. All triangles with like this one, the red one, which have a side parallel to this diagonal, are short ones with a negative sign. So that's how I remember it. Now, this formula actually is the definition of the determinant for this particular matrix. And next lecture I will probably spend to analyze the formula, its properties, and how it affects the system of coordinates transformation and equations, systems of linear equations. All right, so now the same thing actually which I was just explaining is in notes on Unizor.com, and I do recommend you to go through this again, just by yourself. It might actually contain certain more details, but basically it's exactly the same thing. Again, next lecture will be dedicated to properties of this determinant for 3x3 matrices and some comments about it. That's it for today. Thank you very much and good luck.